Today, we're dissecting the insanity of building a foundation model, not the glossy, we trained GPT-5 press release, but the brutal reality where your training run costs $50 million, your data pipeline corrupts at 80% completion, and your model decides that hello should be answered with 47,000 tokens of gibberish. 3 experts who have survived the foundation model trenches, burned through venture capital faster than a crypto startup, and learned why just scale-up BERT leads to bankruptcy. I'm Sam, and someone just asked me why building our own LLM costs more than our entire company valuation.
I've architected 3 foundation model projects. 2 failed spectacularly, 1 barely succeeded. The gulf between let's train a language model and actually shipping a useful foundation model is filled with engineering nightmares, infrastructure costs that would make Netflix jealous, and the humbling realization that data quality matters more than model architecture. Foundation models aren't just big neural networks, they're complex distributed systems that happen to do machine learning.
My job is making foundation models economically viable. When your training run requires 10,000 GPUs for 6 months, every optimization matters. I've seen companies burn through $100 million in compute costs to produce models that barely outperform GPT-3. The infrastructure challenges are insane distributed training, fault tolerance, data pipeline scaling, and the constant trade-off between performance and cost. Building foundation models is systems engineering at planetary scale.
I've guided dozens of organizations through foundation model development. The pattern is clear. Those who understand it as a full-stack engineering problem, not just an ML problem, have a chance of success. Those who think it's just training a big transformer typically fail before they reach 10% of their planned training. It's about understanding why your foundation model strategy might be fundamentally flawed from day one.
Dr. Martinez, guide us through this $100 million engineering nightmare. Elena and Marcus, prepare to explain why we'll just train our own GPT is the AI equivalent of we'll just build our own database. No mercy, no hand-waving about emergent capabilities.
Let's start with the fundamental delusion. What's the biggest misconception about building foundation models that both executives and engineers fall for?
That it's a pure scaling problem. GPT-3 has 175 billion parameters, so we'll build a 200 billion parameter model and it'll be better. But foundation models aren't just big neural networks. They're the result of countless engineering decisions about data curation, training stability, evaluation methodology, and architectural choices. Most projects fail not because they couldn't scale, but because they couldn't make good engineering decisions at scale.
The cost illusion. People see OpenAI's success and think we'll just raise funding and train our own. They don't understand that foundation models require sustained compute expenditure over months, specialized infrastructure, and teams of experts. I've seen startups burn through Series A funding in 3 months of training runs that produced nothing useful. The infrastructure alone requires Netflix-scale operational expertise.
Why build a foundation model at all? What's the business justification in 2025?
Control specialization in economics. If you're Google or Microsoft, you need foundation models for competitive advantage. If you're in a specialized domain, medicine, law, finance, existing models might not understand your domain deeply enough. And if you're processing enough data, building your own model can be cheaper than API costs, but most companies don't meet these criteria and shouldn't attempt it.
Data sovereignty and customization. Some organizations can't send sensitive data to external APIs. Others need models that behave in very specific ways that fine-tuning can't achieve. But here's the key. You need to spend $50 million or more to get a model that's competitive with GPT-3. If your use case doesn't justify that investment, you're building an expensive hobby project.
Walk me through the actual steps of building a foundation model. What does the process look like?
Step 1, data collection and curation. You need hundreds of terabytes of high-quality text, not just web scraping, careful filtering, deduplication, quality scoring, and legal compliance. This takes 6 to 12 months and costs millions. Step 2, infrastructure setup. Thousands of GPUs, high-speed networking, distributed storage, fault tolerance. Step 3, model architecture design and hyperparameter tuning. Step 4, the actual training, which can take months. Step 5, evaluation and iteration. Most projects fail at step 1 or 2.
Let's dive into the data challenge. How hard is it to get training data at foundation model scale?
Harder than most people realize. You need not just quantity, but quality and diversity. Web scraping gets you low-quality data filled with spam, duplicate content, and biased sources. You need books, articles, code, conversations, but most high-quality sources are copyrighted. Then you need deduplication at massive scale, content filtering, and bias mitigation. Data curation is often 50% of the project cost and timeline.
In data processing infrastructure, you're not just storing petabytes, you're streaming it to thousands of GPUs continuously for months. Any bottleneck in your data pipeline stops your entire $100,000 per day training run. We've had training runs fail because the data processing couldn't keep up with GPU consumption. Your data pipeline needs to be as robust as your training infrastructure.
What about the infrastructure requirements? How complex is the compute setup?
Insanely complex. You need thousands of GPUs with high-speed interconnects, InfiniBand networking, custom topologies, distributed file systems that can handle petabyte-scale datasets. Fault tolerance is critical. GPUs fail, nodes crash, network partitions happen. When you're spending $50,000 per day on compute, a single point of failure can cost weeks of progress. Most companies severely underestimate the infrastructure engineering required.
How do you handle the training process itself? What makes it so challenging?
Distributed training at this scale is fundamentally different from normal ML. You're coordinating gradient synchronization across thousands of devices, dealing with memory limitations, optimizing communication patterns. Training instability is common loss spikes, gradient explosions, numerical issues that only appear after weeks of training. We've had training runs that looked perfect for months, then suddenly diverged and had to be restarted.
Checkpointing and fault recovery. When your training state is terabytes and you're using thousands of GPUs, saving and loading checkpoints becomes a major engineering challenge. Hardware failures are inevitable. You need robust recovery mechanisms. I've seen teams lose weeks of training progress because they couldn't properly checkpoint their distributed training state.
What are the most common failure modes in foundation model projects?
Data quality disasters. You discover after $10 million in training that your dataset was contaminated with duplicate content, or your filtering removed all the interesting examples. Training instability models that train well for months then suddenly collapse. Evaluation failures. You build a model that looks good on benchmarks but performs terribly on real tasks. Most projects fail because they underestimated the data engineering complexity.
Infrastructure failures and cost overruns. Teams that budget $20 million for compute and spend $60 million because they didn't account for failed experiments, infrastructure downtime, and efficiency losses. Scaling failures. Architectures that work at small scale but completely break at foundation model scale. Resource management failures. Teams that can't efficiently utilize their expensive GPU clusters.
How do you evaluate whether a foundation model is actually good?
This is surprisingly hard. Standard benchmarks don't capture real-world performance. You need evaluation across multiple domains, tasks, and use cases. Perplexity scores are almost meaningless for practical applications. We use human evaluation, downstream task performance, and extensive red teaming. But evaluation is expensive and time-consuming. You might not know if your model is good until after you've spent $50 million training it.
What about the business model? How do you monetize a foundation model?
API services, licensing, or internal efficiency gains. OpenAI's API model works if you have sufficient scale and differentiation. Enterprise licensing works if you have domain-specific advantages. Internal use works if the model saves enough operational costs to justify the investment, but most foundation models never achieve sufficient utilization to recover their development costs. The unit economics are brutal.
How is the foundation model landscape evolving? What's changing the game?
Specialized models and efficient architectures. Instead of building general-purpose models, teams are focusing on domain-specific foundation models, medical, legal code. New architectures like mixture of experts and sparse models promise better efficiency. Transfer learning and continued pre-training are becoming more sophisticated. But the fundamental challenges of data quality and infrastructure complexity remain.
Hardware improvements and better tooling. New AI chips, more efficient training methods, and improved distributed training frameworks are reducing costs, but the scale continues to increase. Models are getting larger faster than hardware is getting cheaper. The infrastructure challenges are evolving, not disappearing.
What about smaller, more efficient models? Are they challenging the foundation model paradigm?
Absolutely, distillation, quantization, and pruning techniques are creating smaller models that match larger models' performance on specific tasks. If you don't need general intelligence, a well-designed smaller model can be much more cost-effective. But you still need the large model to distill from. Someone has to pay the foundation model costs.
How do you handle safety and alignment at foundation model scale?
Safety becomes exponentially harder at scale. You can't manually review petabytes of training data. Alignment techniques like RLHF require massive human feedback datasets. Red teaming needs to cover exponentially more attack vectors. Constitutional AI, safety filtering, and robust evaluation become critical, but most foundation model projects treat safety as an afterthought, which is dangerous for models with such broad capabilities.
What about regulatory and compliance challenges?
Data privacy, copyright, and export controls are major concerns. Training data often contains copyrighted material or personal information. International regulations affect where you can train and deploy. Model weights themselves might be subject to export restrictions. Compliance costs can add millions to foundation model projects, and the regulatory landscape is rapidly evolving.
How do you compete with OpenAI, Google, and other foundation model leaders?
You probably don't compete directly. Focus on specialized domains, unique data advantages, or specific use cases where general-purpose models are insufficient. Open-source models, collaborative development, and novel architectures can create competitive advantages. But trying to build a general-purpose competitor to GPT-4 without massive resources is likely to fail.
What about open source foundation models? How do they change the landscape?
Open source models like Llama democratize access to foundation model capabilities without the training costs, but you still need significant infrastructure for fine-tuning and deployment. Open source shifts the cost from training to customization and serving. It's changing the competitive dynamics. Instead of building from scratch, teams can build on open source foundations.
So building a foundation model isn't just training a big neural network. It's building a distributed computing system that processes petabytes of data, costs tens of millions of dollars, requires teams of specialists, and might still fail after months of work. This is more like building a space program than a software project.
Welcome to the frontier of AI engineering. Anyone can fine-tune a model, but building a foundation model from scratch requires the resources of a major corporation, the engineering expertise of a tech giant, and the risk tolerance of a venture capital firm. Most organizations should focus on using foundation models, not building them.
This episode was brought to you by Engineer Panic, where we expose the brutal reality behind AI's biggest engineering challenges. Because understanding why your foundation model project will probably fail is more useful than believing the hype about democratizing AI. We're back. Let's talk about the practical nightmare of actually succeeding at foundation model development. Elena, what's the most counterintuitive advice for teams considering this?
Don't start with the model, start with the data. Spend 6 to 12 months building your data pipeline, curation process, and evaluation framework before you write a single line of training code. Most teams rush to training and discover their data is garbage after spending millions. Data quality determines everything else. Also, hire infrastructure engineers before ML researchers.
Budget for failure. Your first few training runs will fail, your infrastructure will have problems, your costs will exceed estimates. Plan for 3 to 5x your initial budget and timeline. And build monitoring and observability from day one. You need to understand why your training runs fail, not just that they failed.
Question the fundamental assumption. Do you actually need a foundation model, or do you need the capabilities that foundation models provide? Fine-tuning, RAG, or smaller specialized models might solve your problem at 1/100th the cost. Foundation models are a means to an end, not an end in themselves.
What are the biggest red flags in foundation model projects?
Unrealistic timelines and budgets. Teams that think they can build a competitive foundation model in 6 months with $10 million. Lack of domain expertise, treating it as a pure engineering problem without understanding the ML complexity. Overfocusing on architecture instead of data quality. Missing evaluation frameworks. You can't improve what you can't measure.
Underestimating operational complexity. Teams that focus on training but ignore serving, monitoring, and maintenance. Lack of business model clarity, building a foundation model without understanding how to monetize it. Infrastructure overconfidence, assuming your team can handle distributed systems at this scale.
The build it and they will come fallacy. Just because you can build a foundation model doesn't mean there's a market for it. Most foundation models never achieve sufficient utilization to justify their development costs. Start with user needs, not technical capabilities.
How do you know when to kill a foundation model project?
Set clear milestones and success criteria up front. If your data quality isn't improving after 6 months of effort, or if your training runs consistently fail, or if your evaluation results are flat after multiple iterations, those are kill signals. Also, if your costs are exceeding 2x your budget with no clear path to success, it's time to pivot.
What keeps you up at night about the current state of foundation model development?
The waste, so many teams burning through massive budgets on doomed projects because they don't understand the engineering complexity. The safety implications of democratizing such powerful capabilities without proper safeguards. And the concentration of power. Only a few organizations can afford to build competitive foundation models, which creates dangerous centralization.
The infrastructure monoculture. Everyone's building the same massive, expensive systems. We need more diversity in approaches, efficient models, specialized architectures, novel training methods. The current foundation model paradigm is unsustainable from both cost and environmental perspectives.
The disconnect between capability and responsibility. We're building systems with unprecedented capabilities, but without the institutional knowledge to use them safely. The engineering challenges are solvable, but the societal challenges are just beginning.
How do you prototype and validate foundation model concepts without the full investment?
Start with smaller scale experiments. Build your data pipeline with gigabytes, not petabytes. Test your training code on smaller models. Validate your evaluation framework on existing models. Use this to identify problems before you scale up. Most issues that kill foundation model projects are discoverable at small scale.
Final advice for teams considering foundation model development.
Be honest about your capabilities and resources. Foundation models require expertise in distributed systems, ML engineering, data engineering, and infrastructure at scale. If you don't have world-class teams in all these areas, you're probably not ready. Consider partnerships, open-source alternatives, or focusing on applications instead of building from scratch.
Understand the total cost of ownership. Training is just the beginning. You need serving infrastructure, monitoring, maintenance, and continuous improvement. The operational costs of foundation models are often higher than the development costs. Budget for the full lifecycle, not just the initial training.
Focus on value creation, not capability demonstration. Foundation models are a means to solve real problems, not an end in themselves. If you can solve your problem with existing tools at 1/100th the cost, that's better engineering than building your own foundation model. Choose complexity only when it's the best solution.
This has been Engineer Panic. We've learned that foundation models are distributed computing systems disguised as ML projects, that the engineering challenges are often harder than the AI challenges, and that most organizations should focus on using foundation models, not building them. Sweet dreams, and may your training runs never diverge.
Thanks for the reality check. Now, if you'll excuse me, I need to figure out why our $30 million training run just crashed at 90% completion because someone updated a dependency that changed the tokenization behavior.
And I need to explain to our board why our simple, foundation model project now requires more compute than Google's entire advertising infrastructure, and why we're 6 months behind schedule.
Keep building, keep learning, and keep questioning whether you actually need to build a foundation model. The future belongs to engineers who understand that the most important decision isn't how to build a foundation model, it's whether to build one at all.
This has been Engineer Panic, where foundation models meet financial reality. Until next time, remember, your startup doesn't need its own GPT. It needs to solve real problems with appropriate tools. Choose your complexity wisely.